If we're trying to show that a function is continuous at a specific value c, then we do need to show all three of these parts, that the limit from the left of c is the same as the limit from the right of c, which is the same as f of c. This part is showing the limit does exist. They're approaching the same thing from the left and the right side of c, but then we also have to show that that hole is filled in, that it actually is continuous at c. For example, say I'm given a piecewise function and asked to show that it is continuous at the value x equal to 1. I need to show that the limit as x approaches 1 from the left, so we have to pick out which piece is to the left of 1, and that would be this 2x squared. So that limit is going to be 2 times 1 squared, which is 2. I have to find the limit as x approaches 1 from the right, which is this second piece, the greater than 1, greater than or equal to. It's going to be 2 as well, and then this part always feels a little redundant, but I need to go ahead and show that f of 1 actually does exist because I had that or equal to, and go ahead and show that I understand it would be talking about that second piece as well, so it is also 2. So then I would go ahead and give a conclusion, therefore f of x is continuous at 1 because that limit from the right of 1, the limit from the left of 1 equals f of 1. Sometimes we're going to want to go ahead and say that that also equals 2. If I was being asked for just continuity in general, so not at 1, but just is f continuous, I would also want to make a statement about how I know 2x squared is continuous and the piece 5x minus 3 is continuous because they are both polynomials. Which brings us to this type of question where they give us a piecewise function and then ask what value of k would make this piecewise function continuous. So remember, I've got to check that limit from the left and the right, and then also the value at -3. That's our issue here. And my piece from the left of -3 is this top piece. My limit from the right of -3 is also talking about the top piece. The situation that we have going on here, and it never hurts to just kind of visualize what's happening, is that this top piece has a hole at -3. It looks like that's what's happening, at least. We'll explore it more in a minute. So here's at -3, there's a hole, and then we're wanting to establish k where it actually fills in that hole and is not like above or below it at that -3. So I'm going to start with the numerator here because this is a different type of factoring where that a value is not 1. So remember, I'm multiplying my first and my last term here. So I'm thinking of numbers that multiply to be -6 and add to be a 5 in order to break up that middle term. So a +6 and a -1. And then I'm factoring by grouping, so factoring out a 2x out of this first piece, factoring a -1 out of the second piece. So that leaves us with factors of a 2x minus 1 and an x plus 3. Okay, so then relating this back to what we're trying to do, if that's my numerator, I'm sure you can see this. And then factoring my denominator, I've got an x minus 3, x plus 3. So my x plus 3 is canceled, so there definitely is a hole at -3. And then now I can plug in that hole to figure out what our y value is at -3 for that hole. So in the numerator, we're going to have a -7. The denominator is a -6. So it looks like a +7/6 is where that hole is. So in order to fill in the hole, I need that k value to be at 7/6. Looking at a new example with the exact same instructions, go ahead and see if you can figure out what value of k will make this piecewise function continuous. So pause the video, see if you can find k on your own. So this example is defined where we've got a piece to the left of pi and a piece to the right of pi. So instead of having the hole in one of these functions and plugging it in, we're trying to make sure that the left approaches the same value as the right approaches. So I didn't do this on the last one, but it really is a smart idea if you're trying to show this in a free response problem to make this statement at the beginning that the limit from the left of pi has to equal the limit from the right of pi has to equal f of pi. Just so that you're telling the grader, I understand what I'm looking for. Then we're just plugging in our limit from the left of pi is just plugging in pi into our piece on the left. Our limit from the right of pi is just plugging in the piece pi into the piece on the right. And then simplifying, our sine of 2 pi is 0. Subtracting 2 pi over gives us a negative 2 pi for k. For a function to be differentiable, first it has to be continuous. So for every value, the limit as x approaches a value from the left has to be the same as the limit from the right, which has to be the same as the value at f of whatever that number is. It also can't have any sharp turns or cusps, which algebraically translates to the limit as x approaches c from the left of f prime has to be the same as the limit as x approaches c from the right of f prime. So we're talking about the derivative from the left and the derivative from the right have to approach the same instantaneous slope. So to illustrate this, we're going back to the example that we looked at for continuity earlier, that we checked the limit from the left of 1, from the right of 1, ooh, missing a plus sign, and then also at 1, and it was all 2, so it is continuous. But if we're looking at whether it's differentiable, I need to go on and look at the limit from the left of f prime, which if we're talking about that left piece, I have to go ahead and take the derivative. So I'm talking about the limit as x approaches 1 from the left of 4x, which would equal 4. From the right, I would be looking at that bottom piece, so our f prime for 5x minus 3 is 5. So because we don't approach the same derivatives from the left and the right, it is not differentiable at x equals 1. Our first type, they're giving us a graph. They tell us that there's a vertical tangent at -2, and then horizontal tangents at -3 and -1. And then it asks which values is f continuous but not differentiable. So we're looking at places where there aren't any gaps because it has to be continuous, but there's some reason that it's not differentiable. So looking at this graph, that's definitely happening at 1 because it's continuous at 1, but it has a sharp turn. So that's one of our places where it's happening, continuous but not differentiable. It's also continuous but not differentiable at -2 because it has a vertical tangent line. So there's no way that those derivatives could be approaching the same thing from the left and the right if it's undefined there for the slope. The only other value that it comes into play here is 0, and at 0 it's definitely not continuous. So the only values here are 1 and -2. That makes sense for it to be continuous but not differentiable. We can also have the same type of question that we had for continuity for differentiability, where they have some variables in here and they're wanting to know what values of a and c would make this piecewise function differentiable. So I will start out looking at continuity. I do want to make sure that the limit as x approaches that pi from the left of f of x is equal to the limit as x approaches pi from the right of f of x. So that's just going to entail me plugging in pi into the left piece. So I'll have a pi squared plus sine of pi equal to 2 pi plus c. And I can simplify some things, but I'm not going to be able to actually solve for a c or an a here. I can get it by itself, it's just not going to be completely simplified. So I've got my a pi squared, sine of pi is 0, so I'll just get rid of that. And then I get to a place where I could get one of these variables by itself, but I'm just going to pause. So that's what I get with looking at continuity. Moving on to the piece that is specific to differentiability, I still want to be looking at the limit from the left and the right of pi, but we're talking about f prime now. So that means that I need to find the derivative of each piece of this piecewise function. So my piece on the left, when I take the derivative, I'll end up with 2ax plus cosine. And then my derivative for the piece on the right is just 2. Remember that c value is a number, so if I had like a -7 there, the derivative would be 0. So taking the limit from the left and the right, when I plug in pi, I have a 2a pi plus cosine pi equal to 2. Evaluating my cosine of pi being -1, and then adding 1 over, and then dividing, I get that my a is a 3 over 2 pi. So now that I have a value for a, I can work back to this first equation where I didn't go ahead and solve for c, but I can here, or I can go ahead and plug it in and then solve for c. Really doesn't matter. I'm just going to go ahead and plug in for a and see what happens. So we've got this 3 over 2 pi times pi squared equals 2 pi plus c. So this piece, I'm going to be able to cancel out a pi. So I have a 3 pi over 2, and then subtracting 2 pi. There's c. I do want to go ahead and get a common denominator to see exactly what this is. And when we subtract, we'll get pi over 2 equals c. So it looks like we've got D.